Hello and welcome to the eTech podcast with me, your host, Ryan Morn. I have been involved in the development of electrified vehicles and machines since 2005 as an engineer and a business leader. This podcast is the product of my passion for electric and autonomous vehicle technology. I'm here to share knowledge from some of the world's leading experts as well as my own insights. Join me as we accelerate the transition to cleaner, safer and smarter vehicles and grow the industry around the world.
This podcast, it's the audio from a conference I spoke at called the Industrial Vehicle Technology Electric and Hybrid Vehicle Expo. It's a bit of a mouthful. It's produced by the same guys that do the IVT magazine. So it's the IVT Electric and Hybrid Vehicle Expo. It was held in Germany in November 2017. Fantastic conference. I think the first of its kind, one of the first of its kind certainly, just specifically looking at electrification opportunities in heavy-duty and off-highway machinery. Really very good conference. Lots of major vehicle manufacturers attended. I spoke about Avid's experience with electrification in heavy-duty machinery, in particular looking at low-voltage electrification in off-highway equipment and also high-voltage electrification and the differences between the two and where you'd use one strategy versus the other. So I really hope you enjoy this podcast, and without further ado, let's get on with it.
My name is Ryan Morn. I know some people in the room, but for those who don't know me, I'm the managing director of a company called Avid Technology. You might have guessed, but we're located in the northeast of England, very near to the Nissan plant and very near to Hyperdrive. So just a quick kind of snapshot. Avid's been around since 2005. We do systems electrification for vehicles, a lot of hybrid and electric vehicle developments, but also a lot of work on diesel engines, making diesel engines more efficient. We've got a really good customer base, predominantly heavy-duty vehicles. We typically say we're not automotive, but we've got some quite special automotive customers. And unfortunately, I cannot afford to buy any of the cars that have got our products in. So the topic of the presentation today, actually, this session is all about simulation. And one of the things that we've found in our experience is the simulation guys are typically the enemy. There's been a lot of discussion, and most events you go to now, there's a lot of talk about 48-volt hybrids in passenger car. We're also seeing a lot of potential for that in other sectors, such as commercial vehicles and off-highway. But in addition to 48-volt systems, on a lot of commercial vehicles, you've got a 24-volt DC system as well. So you can do an awful lot of electrification at 24 volts without having to go to 48, but you can do even more electrification at 48 volts. So just some little examples, the opportunities on and off highway machine. So in terms of what we're talking about here is low-level systems electrification. So not a hybrid, a full hybrid, but what you might call a mild or a micro-hybrid. So yesterday, one of the speakers mentioned about the power consumption requirements of the fan system, the thermal management system. That is significant, and it's kind of the low-hanging fruit for electrification potential. We do those systems. Other systems are available, such as the SPAL stuff that's out in the foyer. So there's a lot of opportunities on e-fans at 24 volts and also at 48 volts. Next up is the engine coolant pump, so lots of potential there, and then the other kind of ancillaries. So on a commercial vehicle on highway, you've also got things like air compressors, which you don't tend to have on off highway, and finally to generate the power, but also provide some torque back into the drivetrain, the basic kind of crank assist. So low cost electrical machine. Doing smart power generation, so recovering power under vehicle decelerations or negative torque incidents, and able to put power back into the drivetrain. So really, just to kind of give some examples of where we're at, typical sort of power levels for different devices on different kinds of vehicles. So you can see up in the commercial vehicle end, so typical off-highway engine, 24 volts, you can electrify a lot of those systems. But at 48 volts, you can electrify all of those systems with manageable power levels. We are doing now in the transit bus market systems where we're generating 550 amps at 28 volts with an alternator. So that's actually pretty much becoming the standard in North America. So it's a very effective way of getting some of the benefits of electrification of the powertrain, but without necessarily all of the costs. And I think again and again and again in the last couple of days we've heard people talk about the business case and the return on investment to the customer. So you can actually get some significant efficiency benefits, improvements in engine thermal management, make your after-treatment system work better, but for a very relatively low investment. And actually in some cases what we're finding is we can replace hydraulically driven systems and achieve a cost reduction, or be cost neutral. So if it's so good and so easy, why doesn't every construction machine have electric fans today? We get an awful lot of objections, and this is where the simulation guys become the enemy. So I think this morning there was a really nice example of block modeling approach. So I think most people will be familiar that in particularly commercial vehicles, the way we tend to do our simulations is at steady points of operation. Actually, building a simulation model that covers the full transient operation is incredibly difficult. And as we found several times with customers, even when you think you've built a model which is transient, actually when you dig down into the subsystems, none of those are actually representative of transient operation of, say, the fan system or the pump system. It's actually just basically a lookup table with several fixed points of operation in it. So we encounter these the objections where it's all this standard thing. If you electrify that, it can't be as efficient as directly driving it off the engine because we've got there's conversion losses there, because we're thinking in terms of a fixed operating point rather than the operation under the curve. We can't simulate it easily. Also, the installation of enough electrical power is difficult, and of course, everyone's concerned about adding cost to machines. So I think it's been wonderful to see some of the work that Volvo's been doing on presentations, but I think in general it's quite hard to get buy-in to programs where there's a potential to add cost to some industrial machinery. So that's got to be an important consideration. So just focusing in on that transient operation point, and just picking one specific example being the fan. So what I've got on the left-hand side are two driving cycles. So we can see highly transient operating conditions for the vehicle. And on the right-hand side, I've got a performance curve for a standard engine-driven fan. So I think what you can see from that is there's a peak efficiency point, which actually the efficiency is surprisingly low anyway, even at the peak point, but it drops off fairly sharply either side of the best efficiency point. So when the typical component sizing goes on for an off-highway machine, we tend to be looking at, for the cooling fan, we'd be looking at the peak torque point and the peak power point for the engine, and looking at the coolant flow that was available and working out the fan power that was needed. So we consider those single peak points, but don't tend to look too much at the efficiency under the curve. And actually, when you look at the operation of the machine on the driving cycles or in real world, you see it spends most of its life operating underneath the curve. So this gives us an opportunity when we electrify the components. So yeah, for sure, if you look at the peak operating point, the efficiency of a mechanically driven device is going to beat the efficiency of an electrically driven device. Even if you've got a super efficient, 90% efficient motor electrical conversion system, you've got losses going to electricity, into storage, and then back out to electricity. But the real advantage comes under the transient operating conditions. So if we electrify all of these ancillary systems, we're now free of engine speed. So we can operate the devices at their best efficiency point, and we can keep them there for longer. So a couple of examples of programs. This is the biggest system that we've ever built. So this was a project for a mining truck. So this is an open cast mining environment. We implemented an electric fan array. So you can see we've moved from a single large fan, so the standard engine-driven fan on this truck is about 2 meters in diameter. And we're actually now using what to some people looks like a ridiculous number of small fans. And there is an advantage from an efficiency point of view in going to an array of small fans, even though it's counterintuitive with the fan laws. The other thing that we've done is we've moved the fans to the outside of the system, so they're now pushing cold air through it, which also has an advantage. And in total, there's about 20 fans on that truck. And you can just about see one of my colleagues standing next to the system there, so it really is a giant of a thing. So the interesting numbers on this, we achieved 70 kilowatt power saving, peak power saving, and that actually translated into about 15% fuel saving in operation. Just because we could control the fans much more easily, they were no longer connected to engine speed, and we can do some neat tricks with them in terms of being able to flow in reverse as well. So quite a lot of potential there. Next example is an off-highway tractor. So this was an OEM project. We have a very close relationship with an American company. They did this in conjunction with the OEM. I think one of the main objectives here was to get to a single plane cooling pack. So we talked again a lot over the last couple of days about coming up with a user case, a user benefit. So on agricultural machines, the cooling packs get blocked up really easily with debris from activity or dirt from the ground. So the target here was to go to a distributed cooling system, which the customer did very successfully. You can't really see, but actually on top of the engine there's heat exchangers with cooling fans mounted underneath them as well. So this 27 kilowatts peak power saving compared to the standard system achieved full load cooling performance. Did use quite a lot of fans again. So in terms of the sort of the next system being the engine coolant pump, we're just starting to see that get some traction in commercial vehicles, but it's fair to say in passenger car, BMW were the trailblazers with this a number of years ago. BMW, though, they took a fairly radical approach, and I'm not sure if this is the reason they did it, but essentially when they launched electric engine coolant pumps, they did a complete redesign of the engine. So if you look at any of the new BM engines that have electric coolant pumps, they have a cross-flow design on the engine to reduce the pressure drop, and the reason they would, the benefit of that from the pump point of view is it reduces the pump power, so it meant they could get to a manageable pump power at a 12-volt system. Okay, but there's not many people, particularly in industrial vehicles, who are going to do a new engine design from scratch and go to a cross-flow cooling system just to facilitate an electric pump. And really, that's where the 48-volt systems come in. So if we go to a 48-volt bus, we can implement an electric engine coolant pump very simply on a very, very wide range of engines. So the biggest pump that we're working on at the moment is a 12 kilowatt electrical power cooling pump for quite an enormous engine for an off-highway application. But 24 volts, you've got a lot of potential for electric pumps as well with standard engines. It depends on the pressure drop in the engine and the cooling system. So again, the advantage of electrifying the engine coolant pump is you're free of engine speed. So clearly, if you look at it, it's not as efficient at the peak operating point. But like I said before, the peak operating point isn't where we're spending most of our life on an off-highway machine. So by decoupling the pump from the engine speed, we can operate the pump at full speed when the engine's idling, so we can have improved performance of the system. It's more efficient to use higher coolant flows than higher air flows for engine cooling. So we can really optimize the thermal management system by balancing out the performance of the pump and the performance of the fans, whereas in the past, if you had engine-driven components, there wasn't a lot you could do in terms of controlling them and turning them on and off. So it's a significant exercise. It definitely, I think one of the downsides to electrifying the main engine coolant pump is you need the buy-in of the engine manufacturer. And for some companies, Volvo for instance, they make their own engines, so that might be easier than for others, particularly in the industrial vehicle space, where oftentimes you're buying in engines from third-party suppliers. But there are electric pumps coming through on some of the third-party engines now. So what are the other benefits of low-voltage electrification? So it's really, I've used the acronym RDE, but real driving, so real-world operation of the vehicles. We've been involved in electrifying subsystems on diesel engine vehicles now for almost 10 years. We've got a lot of experience with the real-world operation of those systems, and freeing them from engine speed provides a lot of benefits. One of them being it supports start-stop engine operation. So we heard about some start-stop benefits earlier today. All of those cranking, so every time you start the engine, you've got to crank it. If you've got lots of loads hanging off the engine in terms of fans and pumps and other bits and pieces, that adds to the cranking load. So you're putting more stress on your starting system. If you take all of that out and make it free of the engine, you can start the engine easier. On a vehicle with a power steering system, you need electric power steering, because if you stop the engine, you get a bit of a kickback from the steering wheel if it's an engine-driven pump, particularly on a diesel. So we can do quite a bit of engine downsizing. So in off-highway, it really depends on the kind of vehicle you're looking at, but in some of the applications, the parasitic power consumptions of the thermal management system and the other accessory loads are really significant compared to the total engine power. So we've seen the ability, by going to a mild hybrid configuration where we've got electrified ancillaries and only a very small amount of electrical torque infill, we can downsize the engine by a full engine class. We have improved thermal management capabilities as well. So I think off-highway market, cold operating cycles are a big problem for SCR systems. So the vehicle's having to go into forced regen a lot because basically the engines don't get warm enough, the exhaust isn't getting warm enough. So being able to actually force the engine to run at a higher temperature by controlling the coolant flows and the airflows much more accurately is a big operational benefit. So improving safety might seem like a strange thing. I think in some markets where we operate, there's a big issue in terms of risks associated with hydraulic system failures. So particularly the transit bus market, there's been a big issue with bus fires being caused by hydraulic system leaks going onto the engine. But the improved controllability of the electric accessories means you can do a lot more. We're also seeing, it's quite interesting, on high voltage electric and hybrid vehicles, people opting now to go for 48 volt accessories. So instead of having an air compressor or a hydraulic pump operating at high voltage, they're going for a sort of 3 voltage system for the electric and hybrid powertrain. So you've got your low voltage 12 or 24 with the conventional, your lights and your dashboard and things on. Then an interim voltage of 48 with the higher power consumers sitting on that, and then the high voltage for the traction system. And I think that's all about cost management on the vehicle. There are some interesting things with the 48 volt accessories on some motorsport applications where it's all about performance and light weighting, which isn't really such an issue on off-highway. And the other thing with low voltage electrification, it's really an enabler. Some things that we've always wanted to do but couldn't because we didn't have the electrical power before, such as e-boosting, electric valve actuation, and both of the common types of waste heat recovery system that are out there. They really it becomes much more feasible with a 48 volt bus on the vehicle. So there are some significant other benefits that come into play. There are challenges. So other than the common objections that we get, there's actual challenges in terms of the hardware and the system architecture. There's a new standard for 48 volt systems, LV148. It's gaining a lot of acceptance and pace, but it's not a fully formed standard yet. The main kind of obstacle really is the energy storage system. So what you really need is a very cost-effective battery pack. So if you're considering moving to a 48 volt architecture, I'd suggest talking to Chris. getting access to some of those wonderful Nissan low-cost, high-power cells in an off-highway specification battery system. When we do the math on this, it always works out great with all the accessories. The electrified ancillaries are actually not that expensive and can be cheaper than the equivalent hydraulic parts. But typically, things start to get difficult when you add in the cost of the energy storage system, which is quite difficult. A 48-volt high-power system is difficult to do. There is issues in terms of component supply at hardware and a silicon-level 48-volt systems and getting actually access to stuff, the sort of supply lead times. And then really the ability to perform accurate simulations. So we've been involved in 2 OEM projects now where actually what's happened is after 6 to 9 months of attempting to get simulation models working, we've actually given up, just stopped, said, right, this would be easier just to build something on the test bed and go and test it. The simulation guys are going round and round in circles, not able to look at the full model. It's been really surprising when you sort of dig down deep in, you look at the engine model, and there'll be a good transient thermal model for the engine, but everything else is based on lookups, so it doesn't come out with sensible information when you start to look at doing this sort of level of electrification. Okay, so quick summary. So there are some good benefits to be had in off-highway through electrification. It doesn't have to be high voltage. Doesn't even have to be 48 volts. There's a lot you can do at 12. There's even more you can do at 24. 48 is brilliant. We do love avid high voltage hybrid and electric vehicles as well, by the way. We're not against that. And that's it. Okay. Thank you.
Okay, so thanks very much for listening. Don't forget to subscribe. Please leave us a rating or hit like, depending on which platform you're listening on. It really, really helps us to extend the reach of the podcast and get out there in front of more people. Thanks very much. And look forward to speaking to you again soon.